Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This lesson is going to look at phase equilibrium for multi-component systems. Our goal here is that you'll be able to describe the criterion for phase equilibrium in these multi-component systems by the end of the lecture. Earlier, we had looked at the basic calorimeter problems, and one of these was the mass flow equilibrium. In this case, we had a calorimeter, which is an insulated, isolated device with material on the two sides, made up of a binary mixture for the sake of simplicity. The partition between the two sides was rigid and semi-permeable to component 1, so one molecule only could move back and forth between the two sides. It didn't really matter whether or not we chose to have this as a conducting or adiabatic partition because energy, heat will transfer because of the molecules moving sides. So as a result, we have that the change in number of moles on side A and side B will be equal in magnitude but opposite in sign. And similarly, the internal energy on sides A and B will be equal in magnitude but opposite in sign. And as we look at how we maximize ds, for these two sides, the sum of sides A and B ends up giving us an equation that can only be true at equilibrium, so ds equals 0, if we have uniquely that temperature is equal on both sides and that the chemical potential was equal on both sides. We also now have been looking at various relationships for expressions for energy, but we'll look specifically at the Gibbs energy right now. So dG as a function of temperature, pressure, and number of moles can be defined in terms of partial derivatives. So it's dG dt times dt, dg dp times dp, and the sum of dg dn times dn for all of the various components. If we then look at this on a specific Gibbs energy basis, dividing through by the number of moles, we get a similar expression, except that the dg dni becomes the partial molar Gibbs energy, and then the dni becomes dxi. Okay, but we also know from our fundamental relation that dg is negative sdt plus vdp plus the sum of the mu i's dxi's. And so from this we can say that dg dt at constant pressure and mole fractions is going to be negative s, and dg dp at constant temperature and mole fractions will be v. But more importantly, we can say that the partial molar Gibbs energy is the same as the chemical potential. Now, if I fix the temperature and pressure, because we've already seen through other analyses that at equilibrium the temperature and pressure will be constant. Then I end up with looking at dG for two phases in equilibrium, that dG is the sum of the partial or the changes in Gibbs energies for the two sides, and that'll be 0 at equilibrium. The number of moles between the two phases, if one increases, the other must decrease, because the number of moles in a closed system will be constant. And I end up with that the Gibbs energy, therefore, of the two phases, or the partial molar Gibbs energy of the two phases, must be equal for every species I in order to guarantee that dG is 0 at equilibrium. We also frequently state this as that the chemical potentials of the two phases will be equal for every component at equilibrium. So these are our primary criterion for phase equilibrium. We usually do it in terms of the G variables, constant temperature, pressure, and partial molar Gibbs energies for every species. In next lessons, we'll start looking at ways that we can extend these definitions for some other important systems. Thank you.